Hi there! In the previous Arduino video we tried to generate audio signals with the help of the embedded function tone, which emits a square wave at the requested frequency. We also tried to generate signals different than square waves with the help of a wavetable. However, the wavetable experiment failed because I couldn't make the Arduino run fast enough to generate waves at a reasonable frequency. Thanks to the help I received from the comments to that video, I made some improvements to the circuit and to the software, and now I am going to share with you the new findings. Let's begin! You can see that this circuit is very similar to the one used in the previous episode. There are only a few changes to make the experiments easier to run. First, I removed the possibility of selecting the shape of the signal. Since I decided to concentrate on the signal generation, I just forced a single shape in the software itself. To change the shape, we just need to update a variable in the software and then recompile. Second, I used the pin from D0 to D7 for the 8-bit output that goes into the digital to analog converter. I did so because that way it is going to be easier to control the pins simultaneously, which will speed up the software execution. More on that later when we will take a look at the software. Third, I used a voltage follower at the output of the digital to analog converter, so now we don't have to worry about drawing too much current from it. And fourth, I added a mixer to the circuit to add a negative DC component to the signal to cancel out the positive component already there. And this mixer takes the place of the capacitor used in the previous circuit. Why not, since I had an extra op-amp available in the LM358 IC that I used. All the tests I executed involved the use of this potentiometer on the left. The Arduino will still read the voltage at the cursor of the potentiometer to determine the frequency of the signal that is being generated. The voltage is read periodically and the frequency is updated in real time. Here is the code for the first experiment that I ran. Here we have the same wavetable used last time. These three variables determine the sample to read in the wavetable and the number of samples per period. Right now I assigned a 2 to the variable column, which corresponds to the sine signal. Changing this value will allow us to change the shape into either the rectangular or the triangular. The setup function will simply set the value of the variable row for the first sample in the wavetable. It will also set the embedded variable ddrd to the binary number 11111111, 8 ones. The variable ddrd is actually a register that defines how the pins from D0 to D7 will be used in the program. A bit of 0 means that the pin is set for reading, a bit of 1 means that the pin is set for writing. In our case, all the 8 pins from D0 to D7 are set for writing, since they are those that will be used to output the digital value of each sample. In the previous episode I used a loop to write the pins one by one, but this time we are using the internal registers of the microcontroller, which are capable to address all the 8 pins at the same time. The DRD is the register that controls how the pins work. The loop function will need to do two things. First, it will need to read the voltage at the potentiometer cursor to calculate the frequency of the output signal. And second, it will need to apply a delay between one sample output and the next, so that the correct frequency can be generated. And third, it will have to write the digital value of the sample to the 8 output pins. That can be done acting simultaneously on all the pins through the internal register port D. Let's now go to the lab to see how the use of these two registers help in the generation of the output signal. So here is the setup for our experiment. So here we have the Arduino UNO over here, already connected to the digital to analog converter over here, and to the two op-amps over here. We need then an oscilloscope, which will allow us to see the signal emitted by the Arduino, And here is the computer that will allow us to upload the code that we just analyzed on the Arduino. So let's do that right now. And so let's push the code onto the Arduino UNO. The code is uploaded. So now we connect the oscilloscope to the output, which is on the pin 1 of the op-amp, and then we take a look at the oscilloscope. And look at that, we can actually see a sine wave. This seems much better than what we saw in the previous episode. We weren't able to do that at that time, but look at this now. The sine wave is there, you see the signal, it seems like broken in pieces, but in reality if we expand this, you see these are actually the samples that are generated by the Arduino based on the contents of the wavetable. And since we selected for the wavetable the sine wave, here it is. Right now we have we are all the way on the left with the potentiometer, and so we have the minimum frequency on the output of the Arduino, which is about 3 Hz, between 3 and 4 Hz. Let's now try to increase the frequency with the potentiometer, and let's see what happens. I'm rotating the potentiometer. You can see me doing it right here, but apparently it doesn't do any good with the output signal. So, okay, we got an improvement with respect to the code of the previous video, but still we are not able to make any good use of the Arduino to generate variable frequencies. So, summarizing, the result of this test tells us that the use of the internal registers DDR-D and port D help in saving some time in the execution of the code on the Arduino. However, this savings is not quite enough yet. Although we can now see some improvements in the frequency and the shape of the wave that we can now obtain, we cannot still increase the frequency. Let's try something else now, and let's see if we can do better. Let's start with separating the functionality of reading the voltage of the potentiometer and calculating the frequency, and the functionality of writing the sample value of the wavetable to the output. So, instead of reading the voltage every time the delay for writing the output expires, we read the voltage at regular intervals, thus reducing the frequency of such reads and making them happening at regular and longer intervals. This will help in reducing the amount of voltage reads that we do every second. To do that, we use one of 3 timers available on the Arduino UNO, in particular the timer T2. This timer is an 8-bit timer which increments every 62.5 nanoseconds. But, well, wait, I'm going too fast. Let me do a step back and let me explain first what a timer is and how we can use it. The ATMega 328P, which is the microcontroller at the core of the Arduino UNO, has 3 different hardware timers in it, called Timer 0, Timer 1 and Timer 2. Yeah, no fantasy at all. Each timer is associated to a register that stores the value of the counter. These registers are called TCNT0, TCNT1 and TCNT2. Let's concentrate on timer T2, which is the one we will use right now. The other timers work similarly, although each one of them has some peculiar functionalities that distinguishes it from the others. Timer 2 in particular, like we said, has a counter of 8 bits, and so it can reach a maximum value of 255. The counter is incremented at each system clock pulse, and when it reaches the maximum value, it restarts from 0 at the next pulse. And so it counts like this: 0, 1, 2, 253, 254, 255, 0, 1, and so forth. The counter never stops, and it is handled directly by the hardware. Since the Arduino UNO clock runs at 16 MHz, it means that we will have a pulse of the clock every 1/16 MHz, or 1 every 62.5 nanoseconds. With a clock so fast, the count will reach the maximum value every 15.94 microseconds. A little too fast for what we need. But fortunately it is possible to slow down the count using another piece of hardware element inside the ATMega, known as the prescaler. The prescaler takes the input of the system clock, divides it by a certain amount, and outputs a new clock at a lower rate. The prescaler is a programmable unit inside the ATMega, and we can set it to some prefixed values, and these are 1, 8, 32, 64, 128, 256 and 1024. When the prescaler is set to 1, it will output a clock that has the same speed as the system clock. In our case, we will program the prescaler to divide the system clock by 1024, thus obtaining a new clock at 15.63 kHz, which means that the counter will be incremented every 64 microseconds. And so, the maximum value of the counter will be reached every 16.38 milliseconds, which is a much greater value than the original one of 15.94 microseconds. But what do we do now with this counter that keeps incrementing and restarting from 0 every time it reaches the maximum value? Well, here is the other important thing about timers. It is possible to program them in such a way that they can generate an interrupt every time a certain condition is verified. In our case, we will program our timer T2 in such a way that every time the counter reaches a certain value, it will trigger an interrupt, and at the same time it will reset the counter back to 0, even if the max value has not been reached. We just need to set the appropriate bits in certain internal registers, and the hardware will do the rest, using logical ports appropriately connected to provide this functionality. There is much more to say about timers, and we would need several hours to go through to the details of the whole functionality. So at this point I will stop here, since I have described the details that we need. But if you want to know more, the best way to learn is to get a copy of the ATMega 328 datasheet and look for the section about timers. It is a large document, 294 pages long. Let's take a look at the code I wrote to handle the voltage reads at the potentiometer using timer T2. Let's start from the setup function. At the beginning, we see again the settings for the first row of the wavetable and the pins D0 through D7. Then there are a few lines of code to set the appropriate bits for the use of timer T2. First of all, we execute the instruction no interrupts. This instruction disables the handling of the timers by the ATMega, and this is necessary to be able to prepare all our settings for the timers without any interference from other interrupts that could be currently set. Then we initialize to 0 the two registers that control the functionality of the timer, and they are TCCR2A and TCCR2B. Once they are set to 0, we can later set the configuration bits that we need. Next, we initialize the counter TC and T2 to 0, and so the system can start the timer from the beginning. Next, we define the value at which the timer will trigger the interrupt using register OCR2A. The value is currently set to the maximum, 255. This will allow us to experiment with different values without making any other change to the code. We just need to change this single line. Next step is to set to 1 the bit that defines the CTC mode, which is the mode that compares the counter with the OCR register, triggers the interrupt on a match, and finally clears the counter to start a new cycle from the beginning. Another thing we need to set is the actual timer compare interrupt, which is done through bit WGM21. Then we need to set the prescaler to 1024, which is done through bits CS22, CS21 and CS20. And finally, we need to set the mask for the timer compare interrupt. This is the bit that allows us to enable and disable the specific interrupt without changing anything else on the configuration. And yes, for those of you who know what a maskable interrupt is, this is exactly that. And now that the configuration is all done, the interrupts can be re-enabled by calling function interrupts. And now, once the interrupt will be triggered by timer 2, the ATMega will automatically stop whatever else is doing and will call a function to handle such an interrupt. This function is called ISR, and it needs a parameter that identifies the timer being used and the mode of the timer, which is the compare match interrupt. This is the function, and what it does is calculating the frequency of the signal we want to generate, based on the reading of the voltage of the potentiometer. So, with all of this, we have just isolated this functionality in its own function, and the function will be called periodically every 16.38 milliseconds without the need of the delay function. However, the delay function is currently still used inside the loop function, exactly the same way it was in the previous test, but this time just to output the 8-bit sample to port D, which handles all the pins from D0 to D7. Let's now bring this code to the lab to see if this change brings any benefit to our audio generator. So this is the code for the second test, and this time again you can see that I have a timer set up here, which is timer 2. And so let's upload this code to the Arduino now and let's see how it behaves. Okay, the code is uploaded. Let's take a look now. Again, we are here with the potentiometer all the way to the left. Let's go to the oscilloscope and let's see what we see. And there is still a sine wave. This time is quite faster, it's 18 Hz. And let me try now to move the potentiometer to see if we can do it better. Oh, look at that. This time I can actually change the frequency. So, the timer, along with the interrupt, have done something useful. However, I can see if I go up over a certain amount, I'm still having trouble. You see, I cannot pass the threshold of 200 Hz. Still very low, and if I move high enough, things get really weird. So, okay, now I can control the frequency, but still I cannot do much of it because the control is very limited to just a few tenths of hertz. If I expand here, you can see that still we have the samples of the sine wave, so we are still using the wavetable correctly. There is some wobbling over here, probably because we are still using the delay function for actually outputting the signal out of the Arduino. Okay, it looks like this prototype works a little better than the first one, but the frequency of the signal still cannot be increased much. Fortunately, we still have some space for another improvement, eliminating entirely the use of the delay function. Let's see how this can be done. To entirely eliminate the delay function, all we need to do is to use another timer to define how long to wait to write each sample from the wavetable. Since there are 64 different samples for each period of the output signal, we will need to wait 1/64th of the signal period between each sample. Since this requires a better resolution of the timer, we will use timer 1, which is a 16-bit timer. We will use this timer exactly the same way as timer 2, but for a different purpose, so its ISR function will have to do something different than the one for timer 2. The main differences are therefore in the new ISR function and the setup function. Let's start with the setup function. The beginning of it reflects exactly the one from test 2. However, at the end of the function, we have the instructions to set the new timer 1. Again, we start with the reset of the control registers to 0. We initialize the counter to 0, and we initialize the output compare register to 255. This register later on will be modified to reflect each new frequency read executed through timer 2. Next, we set the control registers. In particular, we set the bit for the CTC mode, we set the prescaler, which for this timer is set to 8, since we need a bigger resolution. Then the mask is set to enable interrupt, and the interrupts functionality of the ATMega is re-enabled. I made a little change to the ISR function for timer 2. Now, besides the reading of the voltage and the calculation of the frequency, it also needs to calculate the comparison value for timer 1. I explained all the details in the comment, but basically, given the actual frequency, the number of samples within the period, the system clock frequency and the prescaler value, I calculated a conversion factor to convert the frequency in the OCR value, which is then set at line 81. The ISR function for timer 1 will only need to increase the sample number, which is the row of the wavetable, and then output the sample on port D. And what about the loop function? Yes, it's empty. We don't need anymore to do things repetitively in that function. Now everything is dealt with the timers and the corresponding interrupts. Let's see how this final version of the software works in actuality, running another test in lab. And here is the next code, where this time we have two timers. Timer 2 to basically read the frequency from the potentiometer, and timer 1 to generate the signal from the wavetable. So let's upload this one on the Arduino, and let's see how it behaves. So the potentiometer is again all the way to the left. Let's go take a look at the oscilloscope, and we have right now a frequency of 20 Hz, which seems quite stable now. So let's move the potentiometer and to increase the frequency, and let's see what happens. So right now we are at 150 Hz, 270, 300. Look at that, 400 Hz, and we still have a nice sine wave, although there is still some shaking on the wave. The generation is not perfect yet, but look at that. I already reached 1.4 kHz, and I can probably go even higher. Let's see if I can do that. So 2.4, 3.5, and this is the maximum that I can achieve. Now the potentiometer doesn't give me anything else. So we are at about 3.5 kHz with this code, and the sine wave is there. Looks nice. As you can see, here are all the steps of the sine wave, each one given by a sample, and we still have this kind of things around. So something is still not perfect with this attempt. Well, it looks like this new software that only uses timers works much better than the previous two versions. So much better that we can now reach a frequency of the output signal around 3 kHz. Unfortunately, this is still not what I originally had in mind. My hope was to be able to reach frequencies above the 6 kHz, and we are still far away from that goal. It looks like the new improvements suggested by you guys were very beneficial. Still, we are not yet in the range I needed for my next project. Yeah, I didn't tell you, right? All these experiments were needed for another project that I have in mind, but I am not going to tell you what the project is going to be, not yet at least. For now, I will leave you with the suspense. Right now, let's just say that I will need to run more experiments, and probably the next step will be to change the microcontroller altogether. Maybe I could try with the Arduino UNO, which has a system clock about 7 times faster than the Arduino UNO. Or maybe I will look at an entirely new family, like the teensy boards, as it was also suggested in some comments on the previous video. The experiments will continue, stay tuned, subscribe to the channel and click on that bell to enable the notifications to avoid missing the next episodes. Thank you for watching this video and as usual, happy experiments!